Hello Angela, this is Adam Hall, your master's student. As you are already familiar with my research in robotics, I thought I would share an interesting project I did for my chemistry thesis at Queen's University while working under Dr. Nick Mosey and Dr. Anne Petit-Jean. In this project, I explored the pH sensitivity of a molecular switch that has applications in targeted drug delivery. In general, when people consume a drug to combat a disease, it is delivered to all their cells, both healthy and diseased. This is inefficient and can cause undesired effects. For example, hair loss during cancer treatment is a side effect of the drugs adversely affecting healthy cells. Targeted drug delivery aims to deliver drugs only to diseased cells. This reduces the side effects of dangerous drugs, helps keep them within proper therapeutic ranges, and can increase the drug's efficacy. One way to perform drug delivery when treating cancer is to exploit the fact that cancerous cells are slightly more acidic than healthy cells. In the diagram, the purple shape represents a drug delivery molecule and the red shape represents the drug. At pHs close to the healthy cells, the drug delivery molecule and the drug are bound together. In the more acidic environment, the drug delivery mechanism reacts to the additional protons in solution, changes its shape, and releases the drug. pH sensitivity is a common mechanism for cancer drug delivery. In this work, we consider a molecular tweezer as our drug delivery mechanism. In neutral environments, the large, planar arms are attracted to each other. Many cancer drugs are also planar and neatly fit in between these closed arms. Once in a sufficiently acidic environment, however, the nitrogen binds with a proton, which attracts the oxygens on each arm, forming hydrogen bonds. These hydrogen bonds are stronger than the planar interactions, rotating the arms, opening the tweezer, and releasing the drug. In order for this tweezer to be used for cancer delivery, drug designers need to be able to tune the pH at which the tweezer opens, so that it will only deliver drugs to cancerous cells. We formed the hypothesis that the switching pH could be tuned by bonding different chemical groups in the R position shown in the figure. Each group has different electron withdrawing or donating effects, changing the nitrogen's ability to accept a proton. Thus, the objective of this work was to determine how different chemical groups changed the switching pH of this molecular tweezer. First, we performed a computational investigation into our hypothesis. For each chemical group, we computed the energy difference between the open and closed conformations of the tweezer. This energy difference is directly related to the pH at which the tweezer should open, as given by the equation on the slide. This plot shows the relation between electron withdrawing or donating ability and the change in conformation energy. All energies shown here are with reference to the tweezer with no chemical group. The more electron withdrawing a chemical group is, the more negative the change in energy is. The more electron donating a chemical group is, the more positive the change in energy. This relationship supported our hypothesis that pH switching could be controlled with different chemical groups. Next, we aimed to confirm our computational results through experimentation. We decided to synthesize a tweezer with an ammonia group, NH2, as it was one of the strongest electron withdrawing groups and could easily be transformed into another chemical group for later use. Once synthesized, we performed NMR titration to determine the pH at which switching occurred. Synthesis of the compound proved tricky, but after trying a technique called Suzuki-Miara coupling, we managed to yield a sufficient amount of product for the study. Nuclear magnetic resonance titration was able to tell us the pH at which switching occurred and was seen to switch at a pH of 11. This is highlighted in the red box. This was higher than the tweezer with no chemical group, as predicted by the computational model. In conclusion, this work was able to show, through both computational and experimental investigations, that the more withdrawing a chemical group is, the higher the pH of switching will be. Future experimental work with additional chemical groups needs to explore the range by which the pH can be tuned. Thank you for listening.